In this video, we'll see more examples of the chain rule. Just as a reminder that what the chain rule was, uh, it's just a reminder. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. Sometimes, as you know, y might be a relatively complicated function of x. So instead of finding the derivative of y directly with respect to x, we introduce a middle function u, and the derivative of y with respect to x, the left side, is going to be the derivative of y with respect to u times the derivative of u with respect to x. So let's see some examples that uh, we use the chain rule. Suppose y is radical of 10x minus 3. And I want to find the derivative of y with respect to x, or just y prime. And if applicable, we need to simplify our answer. I would suggest that you pause the video and try to find the answer on your own before watching my solution. So for this function, y equals radical of 10x minus 3. That's a given function. Uh, the complication comes from the fact that under the radical, we don't have just a variable. We have a function of the variable, the 10x minus 3. So to make it easier that we can use the chain rule, we let this expression under the radical be the new function u. So u is 10x minus 3, and therefore y is going to be what? Radical u. So if I let 10x minus 3 be the new variable or the new function u, then y is radical u. Using the chain rule, now we are ready based on that to use the chain rule. What we are looking for was this. We were looking for dy over dx. Using the chain rule, this is going to be the derivative of y with respect to u times the derivative of u with respect to x. So what is this part? The derivative of y with respect to u. That's come from this function. Y is a function of u. And as you have seen before, using the power rule, the derivative of radical u is 1 over 2 radical u. Just as a reminder, to find the derivative of radical u, we look at radical u as u to the power of 1/2, and we use the power rule. You have seen this before when you learned about the power rule. Also, we can find the derivative of u with respect to x because u is 10x minus 3. That's quite simple. If u is 10x minus 3, the derivative is just 10. The derivative of 10x minus 3 is just 10. So let's see how we should show our final answer. So 10 times, so the product of these two things, 1 over 2 radical u times 10, which make 10 over 2 radical u. Is there any way to simplify? Yes, because 10 over 2 is 5. So let's do that. 10 over 2 is 5. And in the last step, I need a back substitution because the original function was given in terms of a variable x. My answer should be in terms of x. But that's easy because we know that u is 10x minus 3. So that's going to be 5 over radical 10x minus 3. And that's the final answer that should be typed in here. Okay, let's do another example that again the function is in fact a composition of two functions. Y is sine of 5t squared minus 6t plus 1. And I want to find y prime or dy over dx. So using the chain rule, I want to find the derivative of this. Pay attention that the function is sine of that expression. It's not sine times. It is sine of. Previously, when we dealt with derivatives of sine or cosine, it was sine of the variable, like sine of x or sine of t. But it is sine of this trinomial, 5t squared minus 6t plus 1. So the function that we have is a little complicated because it is composition of a sine function and a trinomial. So sine of 5t squared minus 6t plus 1. We know how to deal with sine of a variable. So let's take whatever we see inside these parentheses as the new variable u. So u, the variable u, on one hand is a function of t because u is 5t squared minus 6t plus 1. But at the same time, y is a sine of u. So u plays two roles. With respect to t, it's a function of t. But with respect to y, it's a variable. Again, we apply the chain rule. Dy over dx is dy over du times du over dx. That's the chain rule. And these two components can be easily calculated. Dy over du, I look at here. Y is sine of u. The derivative of sine is cosine of u. How about the other part? The derivative of u with respect to x. U is 5t squared minus 6t plus 1. We know how to deal with the derivative of the polynomials. That's going to be 10t minus 6. Now we are ready to get to the final stage of this solution. By the way, here I have a cosine function and some polynomial. It's more common to write the polynomial first, so 10t minus 6 first, then times cosine of u. But what was u? I need to go back to the original variable. U is 5t squared minus 6t plus 1. And that's the final answer. So the final answer is 10t minus 6 times cosine of 5t squared minus 6t plus 1. Let's do another example. Uh, Try this example on your own and uh, before watching my solution. So y is cosine of t squared, and I want to find the derivative of y with respect to t. Just one correction in the previous example. In the previous example, what I meant was the derivative of y with respect to t. There was no x here. So let me make that correction here. Sorry for this. So therefore, I need to make this correction here as well. You probably noticed that when I was solving the problem. Here the variable was t, so the question is dy over dt, not dy over dx. So please make this correction. There is no x here. The independent variable was t. Okay. So here the same thing. If when you use the chain rule, the derivative of y with respect to t is the derivative of y with respect to u times the derivative of u with respect to t. But before using the chain rule, we should decide that um, what is taken as u. In the first place, why do we need the chain rule? Because the function is not just cosine of a variable like x or t. It's a function of that variable t squared. That's what makes the problem more complicated. So on one hand, u is t squared. So whatever I have inside that parentheses, cosine of that, I'm let that be u. And y is gonna be cosine of t. Excuse me, cosine of u. T squared was u, so this is cosine of u. Now we are ready to apply the chain rule. Y is cosine of u. The derivative of y with respect to u is, as we have seen before, is minus sine of u. The derivative of cosine is negative sine. And u is t squared. The derivative of t squared is 2t. So now what's the final answer? The product of these two, again, this is a monomial, this is a sine function. It's better to write monomial or polynomial first than the sine function. And there is a negative there, so it makes it minus 2t sine of u. Just one more step, and that is a back substitution. U is what? T squared. So this becomes minus 2t sine of t squared. So the final answer, minus 2t sine of t squared. Okay, so let's see another example. Before the next example, we know that, just as a reminder, that the derivative of e to the x is e to the x. Of course, if instead of x, it's another variable, for instance, if the variable is u, everything will be here u. The derivative of e to the u with respect to u is e to the u. We know this. Now we want to do the next example, having this reminder. Let's y e to the power of 3x, not x, 3x. Find the derivative of y with respect to x. What makes this function more complicated than e to the x is in the exponents, we have a coefficient of 3 for the variable. That's why for doing this, we need the chain rule. In fact, let me rewrite the function here. You can see what should be taken as u. This 3x, we take it as the new variable u. So u is 3x. If I let 3x be just one plain variable u, then y is e to the power of u. So 3x is the same as u, so y is e to the power of u. Now let's try the chain rule. The question was the derivative of y, so dy over dx. We know that by chain rule it is dy over du, meaning that the derivative of y with respect to u times du over dx. Now let's see. Y is e to the power of u. This part, the derivative is, by that reminder, is still e to the power of u. U is 3x. The derivative of 3x is 3. So what's the final answer? So eu times 3 or 3 times e to the power of u. And we know that in terms of x, u is 3x. So 3 times e to the power of 3x is the final answer. 3 times e to the power of 3x. Okay, let's try another example. In the next example, we have an exponential function, but the base instead of e is some other number. In this example, 10 to the power of x. Now I want to find the derivative of y with respect to x. We know how to deal with e to the x. The derivative of e to the x is e to the x, but not when the base is 10. So in the first step, we should use our information from courses like pre-calculus or something like that to rewrite 10 to the x as something as e to a power. As you know, uh, 10 is e to the power of ln of 10. In general, any number b, positive number b, is e to the power of ln of b. Why this is correct? Because the exponential function and logarithmic function are the inverses of each other. So if I look at 10 as e to the power of ln of 10, the whole, and then raised to the power of x. So instead of 10, I wrote it e to the power of ln of 10 and all raised to the power of x. These two consecutive exponents, ln of 10 and x, as you know from basic algebra, they get multiplied. So this is going to be e to the power of ln of 10 times x. ln of 10 is just a constant number. We just keep it as ln of 10. We don't need to use a calculator to estimate the value. Just keep it as ln of 10. So 10 to the power of x is e to the power of ln of 10 times x. But that part was just based on uh, pre-calculus. So this function y, which was 10 to the power of x, is the same as e to the power of ln of 10 times x. That ln of 10 is like a constant. The good thing about rewriting the function in the base e is we can use the derivative formulas or the derivative formula for the exponential function when the base was e. But it requires that the exponent be one single variable, one plain variable. So that's why we let u be this exponent here. So u is ln of 10 times x, and y is e to the power of u. This looks like the previous example. Instead of ln of 10, we had 3 in the exponent, right? 3 times x. Do you remember here? E to the power of 3x. It's kind of similar to that. Instead of u is 3x, u is ln of 10 times x. And y is e to the power of u. The chain rule, the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. This is quite simple because y is e to the power of u, so the derivative is e to the u. The derivative of e to the u is e to the u. How about this part? U is a constant times x. The derivative of a constant times x is just that constant is ln of 10. So ln of 10 is like a k. And when I have a kx, the derivative of kx is just k. So that's why it is ln of 10. So what is the final answer here? It is e to the u times ln of 10. But what is e to the u? I should go back to the original variable. So I'm not done yet. E to the power of u is ln of 10 times x and times ln of 10. But remember that, as we saw on the top, this is the same as 10 to the power of x. Look at the very top. that at the beginning 10 to the x was the same as e to the power of ln of 10 times x. Now I go back and write e to the power of ln of 10 times x as 10 to the power of x. So the final answer is 10 to the power of x times ln of 10, or if you want, you can write ln of 10 first because it's just a constant coefficient, times 10 to the power of x. So the answer is ln of 10 times 10 to the power of x. If instead of 10, there was some other positive base, in the answer, instead of 10, you would have that positive number. I just replace those 10s with the any other base, given base. So from here, I can come up with the general formula for anything of the form of b to the power of x. So let me, based on this, I don't need to repeat the chain rule. There is nothing special about 10. I can do it for any other positive base. So I can come up with this formula that more generally, the derivative of b to the power of x, b is a positive number. The derivative of b to the power of x is ln of b times b to the power of x. This is based on the use of uh, the chain rule. We did that when b is 10. It can be done with for any other uh, base. And at the end, we'll get this formula. So if in a problem, you see the derivative of a number to the variable, you know that by this formula, you know how to find this. For example, if you the derivative of 2 to the power of x, now you can find this easily. If you remember that general formula, the answer is ln of 2 times 2 to the power of x. Let me give an example that we use this formula in regard, and also the product rule. Let me go to the next slide. And please try this on your own before watching my solution. Suppose y is x cubed times 3 to the power of x. The derivative of y with respect to x is what? So I use the product rule because y is product of two functions, x cubed times 3 to the power of x. So using the product rule, this is the derivative of the first function times the second function plus the first function times the derivative of the second function. The derivative of x cubed is 3x squared. And the derivative of 3 to the power of x, we just had this before. The derivative of b to the power of x is ln of b times b to the power of x. So the derivative of 3 to the power of x is ln of 3 times 3 to the power of x. So what's the final answer? The final answer, 3x squared times 3 to the power of x plus the product of x cubed ln of 3 and 3 to the power of x. Since ln of 3 is a constant, it's better to be written first. Ln of 3 x cubed 3 to the power of x. So the answer is 3x squared times 3 to the power of x plus ln of 3 x cubed 3 to the power of x. Let's see another example that, again, we need to use the chain rule. Let y be ln of x squared plus 5x plus 1. It is not just ln of x, it's ln of a function of x. Find the derivative of y with respect to x. Just as a reminder, we know that from before that the derivative of ln of x is 1 over x. Or if instead of x, it's any other variable, like for instance, u, the derivative of ln of u with respect to u is 1 over u. So we have this. Now the function is ln of another function of x, x squared plus 5x plus 1. As you can guess, we let u be x squared plus 5x plus 1. So on one hand, u is x squared plus 5x plus 1. On the other hand, y itself is a function of u. It is ln of u. Therefore, the derivative of y with respect to x, which is by the chain rule, the derivative of y with respect to u times the derivative of u with respect to x, can be easily found because u is a kind of simple function of x and y is a simple function of u. For this part, the derivative of ln of u is 1 over u by that reminder that you see on the upper right corner of the screen. And the derivative of x squared plus 5x plus 1 is 2x plus 5. Now let's see how we can write the final answer. 1 over u times 2x plus 5, so 2x plus 5 over u, but I need to go back to the original variable. U is x squared plus 5x plus 1, so this becomes 2x plus 5 over x squared plus 5x plus 1. So the answer that we need to type in here is this answer. Let's see another example with ln. This time we have a different variable. Suppose y is ln of 2t minus 1. So I want to find dy over dt, not dx, dt. But the variable is t. So the original function is um, a function of t, but ln of not just t, it is 2t minus 1. As usual, I suggest that you pause and try to do the example on your own before watching my solution. So on one hand, I let u be 2t minus 1, and on the other hand, y is ln of u. Again, let's be careful about writing down the chain rule. The derivative of y with respect to t, not x. The respect to t is the derivative of y with respect to u times the derivative of u with respect to t. Y is ln of u, so the derivative is going to be 1 over u. The other part, u is 2t minus 1. The derivative is just 2. So what's the final answer? 1 over u times 2, it is 2 over u. But we should go back to the original variable. U is 2t minus 1, so 2 over, replace u back with 2t minus 1. And that's the final answer. 2 over 2t minus 1.